Continuing on our calculus summer packet, we'd like to take a look at page 5, which deals with, well, first, domain. And what we'd like to do is just review rational functions. Of course, rational functions are ratios of polynomial functions. Uh, you very well might see something like x squared minus 1 all over x cubed plus 4. It's an algebraic fraction, of course, but the numerator is a polynomial and the denominator is a polynomial. And very often we'll deal with rational functions. Given r of x is p of x over q of x, two polynomials, the domain of this rational function would be all x values. Remember, domain is describing what x values can be used, such that the denominator cannot be 0. So let's take a look at one problem in particular. If we needed to find the domain, find all the possible x values that could be used for something such as f of x equals 1 over 3x squared plus 11x minus 20. Well, once again, we're going to realize it's the denominator that we're going to be worried about. We're going to say this 3x squared plus 11x minus 20. We would consider what could happen if it were to equal 0. Really, we don't want for that to happen, but we could pretend we were solving that equation, that it's equal to 0. Let's go ahead and just factor if we could. Of course, the quadratic formula would always be another option. Multiplying the 3x squared, well, we could have 3x and x. 3x times x is x squared. And then we'd say, well, multiplying to 20. Well, my goodness, there are a number of ways you can do that. You can multiply with 1 and a 20, a 2 and a 10, a 4 and a 5. And of course, what we'd like to do is find the correct combination here so that when we use these inner products, we would add up to an 11x. So, dare I say, maybe making this a quick problem, maybe try a 4 and a 5 so that this inner product of 4x and then 15x, remember 3x times 5, this thankfully could add or subtract to an 11. We want to add up to a positive 11. We'd want the 15 to be a plus. We'd want the 4 to be a minus. And in that regard, negative 4 times 5 would multiply to negative 20, and we would be good to go. Set both of these factors equal to 0, and very quickly you will solve, and adding a 4 to both sides here, and then dividing by 3. We'd have x would be 4/3. Here we'd get x is equal to negative 5. And what we'd see here is our domain would be all x values except x could not be 4/3 and x could not be negative 5. All other x values are fine. So that's really what has to be done. Of course, the quadratic formula would have given us the exact two answers. But let's take a look at a little bit of an extension. What if we find the domain of a problem that's even a step more complicated? Let's just say, for example, that we do have a fraction, but then surprisingly, we also have something that's far trickier. We have a square root down below. We have 1 over the square root of x squared minus x minus 20. And at this point, it's true that our denominator cannot be 0. However, even more importantly, this argument, what is inside of the square root, that must remain positive. You must have that being greater than 0. You can't have that expression become negative. You can't take the square root of a negative value. Well, wonderful review. How do we solve a quadratic inequality? Well, much the same way that we'd solve a quadratic equation, at least at first. We need to multiply to -20 and add to -1 using some guessing and checking. Again, maybe working with a 5 and a 4. A 5 and a 4 would multiply to 20, and here we'd get to add to -1 if the 5 was a negative and if the 4 was a positive. And look, even right here, that inner product, drawing in a nose and a mouth, -5x plus 4x would be -1x. For the briefest of moments, we could pretend that this was just an equation, and very quickly kids would tell us, I'm sure, that we'd have 5 and also -4. That being said, we'd know that 5 and -4 would make that expression equal 0. Well, what we're going to actually do is go to a number line. And really, we don't want to equal 0. I'm going to put open circles above -4 and 5. And if you look at this number line, you can see that our number line has been broken into 3 distinct regions, 3 different little areas. We have to the left of -4, we have between -4 and 5, and we also have to the right of 5. I'm going to test a value to the left of -4. I'll test x equals -5. In between -4 and 5, I'll test x equals 0. And to the right of 5, we'll test x equals 6. Now from here, what we can do very quickly is realize that what we are testing is really this original inequality, or we could even have this factored form. That can be a tremendous help to us. I'm going to take those test values and plug them in and see what we get. Maybe using the second highlighted form, plugging in -5, we'd say is -5 minus 5 times -5 plus 4, is that all greater than 0? -5 minus 5 is -10. -5 plus 4 is -1. Is -10 times -1 going to be greater than 0? Well, it is. You have 10 greater than 0. So we'd say yes, and that means that this is true. To the left of -4 will work. If I were plugging in a 0, we could certainly plug that into the same expression as well as the one that was not factored as well. Maybe it's even easier to not factor that test. But plugging it right into this first highlighted form, x equals 0. But regardless, either way, you'd get -5 times 4. Well, that's -20. Is -20 greater than 0? No. Leave it as it is. Let's finally maybe do a little work with testing the 6. As we do that, we can say, well, is 6 minus 5 times 6 plus 4 going to actually get us where we need it to go? And it will, in fact. This 6 minus 5, and this becomes 6 plus 4. Is that greater than 0? Well, they're both positive. You can see 1 times 10, yes, it's going to work. So what's our domain? Well, our domain, you can see the number line would tell us x could be less than -4, or x could be greater than 5. In terms of interval notation, we could say we're going from -infinity to -4, union that with 5 going all the way up to +infinity. And that would be a great way to find out which x values are going to work. One other domain problem I'd like to do before we move on. Let's actually move up, something a little different. For example 3, let's say we wanted to find the domain of something altogether different. Let's say that we had y is equal to the natural log of 5x minus 4. That can also sneak in. Natural logs, as well as any logarithm, is very, very special in that the argument, what is inside of the log, must be non-negative. It can't even be 0. In fact, it must be positive. So we could say 5x minus 4 is greater than 0. Add a 4. We have 5x greater than 4. Very quickly, we'd have x is greater than 4/5. And that would be our domain for example 3. Other points about domain. Square roots demand that the interior, the argument, must be positive. It could even be 0 as long as it's not in the denominator. But odd roots, cube roots, and fifth roots, actually negatives are perfectly okay there. Okay, I'd actually like to stop here and leave off on domain, and we'll pick up next time with asymptotes, which is quite a lot of material as well.